It is late. The rest of the house, the rest of the neighborhood is completely quiet.
Just you and the screen.
Exactly. Your screen is throwing that familiar, harsh blue glow across the room, and you're staring at a blinking cursor in your IDE.
We've all been there.
Yeah. You're an engineer. You are used to systems that do exactly what you tell them to do, like down to the bite. But lately, you've been tasked with integrating a large language model into your stack.
Which is a totally different beast.
It really is. Suddenly, that deterministic world you're so comfortable in, it feels a little bit like you're trying to write code by shouting instructions to a crowded room. You want to level up your AI stack, but all the hype out there makes it sound like this, I don't know, arcane art. Well, tonight, we are stripping away the magic.
Which is incredibly necessary, by the way. I mean, magic is just engineering that we don't fully understand yet.
Right.
When you're building production-level software, you can't just rely on hoping a massive neural network gives you the right output. Because you said, please. You need mechanics. You need predictability.
And that brings us to the mission for this deep dive. We are looking at the absolute baseline of interacting with these models. We're talking about the mechanics of zero-shot prompting.
The foundation.
Yeah, how you get a massive system to do exactly what you want right out of the gate without giving it a single example of what you're looking for.
It sounds totally counterintuitive at first glance. Like,
Yeah.
if I hire a junior developer, I'm going to show them an example of our code base.
Of course.
I'm going to show them our styling guidelines. But with zero-shot prompting, we're skipping all of that context. We're just giving the raw instruction. And understanding why that actually works is the foundational step to mastering prompt engineering.
Okay, let's unpack this. Because as an engineer, before you write a single line of code, you need to understand how the underlying system actually processes a command.
You need to know the runtime environment.
Exactly. You need to know what happens when you hit execute. So, if we give the model 0 examples, how does it have any clue what we're asking it to do?
Well, the secret is that the term zero-shot is, it's almost a misnomer.
Right.
Yeah, it implies that the model is starting from a blank slate, conjuring a solution out of thin air. But it isn't. The model has read a significant chunk of the human internet.
A massive chunk.
Right. It has processed documentation, forums, textbooks, code repositories, translations, summaries. During that massive pre-training phase, it implicitly learned the patterns of virtually every common natural language processing task.
Oh, I see. So it's like calling a function from a standard library.
Yes.
Think about it. When you write a C++ script and you call a sort function, you don't have to define how a quicksort or a merge sort algorithm works right there in your code.
No, we just call it.
Right. You don't have to give the compiler examples of what a sorted array looks like versus an unsorted array. The logic for sort is already baked into the compiler's memory, into the standard library. You're just passing it the data and calling the existing pattern.
What's fascinating here is that that's a powerful analogy, though we should probably clarify the mechanism just a bit.
Sure.
With a compiler, it's a deterministic lookup. With an LLM, the standard library is probabilistically baked into the weights of the neural network. But the functional reality is very similar. The prompt is your function call.
And the training data is the standard library.
Exactly. If you ask a model to translate this text from English to French, it has seen millions of instances of English text followed by French translations. The structural pattern of translation is a deeply etched mathematical pathway. You're just lighting up that specific pathway.
Wait. If the data was always there, if this probabilistic standard library was always full of these patterns from the jump, why did early LLMs fail so miserably at basic tasks?
Oh, man.
I mean, I remember playing with early versions of GPT years ago. If I typed in a direct instruction like write a summary of this article, half the time it wouldn't even answer me.
No.
It would literally just output write a summary of the next article.
Yeah, the classic autocomplete problem.
Pooper.
Yeah, that happens because those early iterations were purely base models. Their only objective during training was to predict the next word.
Right, they were just mimicking.
They were incredibly good at mimicking the internet. But think about how the internet is structured. It's full of, like, lists of questions or lists of instructions on a forum.
Oh, right. So the base model thinks, the user typed an instruction. Usually on a forum or a test prep website, one instruction is followed by another instruction.
Exactly. It was just predicting the next most likely text in a sequence, completely unaware that it was supposed to be acting as a helpful assistant answering a user.
So it's just finishing your sentence, basically.
Yeah, which brings us to the structural shift that makes zero-shot prompting viable today. Instruction tuning.
Okay, instruction tuning. If we connect this, well, sorry, let's elevate the technical reality of this for a second, because I want to make sure we're not just calling it teaching. What actually happens during instruction tuning?
If we connect this to the bigger picture, it's an entirely separate, additional phase of training. The difference between a base model and an instruction tune model isn't just an incremental software patch. It's a transformational shift in how the model behaves.
A transformational shift. How so?
After the model reads the whole internet to learn language, researchers use supervised fine-tuning. They feed the model thousands and thousands of highly structured examples.
Oh, they're physically altering it.
Literally, a user prompt containing an instruction paired with the correct, helpful assistant response. They are adjusting the mathematical weights in the network through a loss function so that the probability of an assistant-like response is heavily favored over a web page continuation response.
Okay, so when you're building an app, you must always use instruction-tuned model variants for zero-shot tasks.
Always.
Trying to use a base model is basically using the wrong tool for the job. To put it in engineering terms, trying to use a base model for zero-shot prompting is like trying to browse the modern web via a raw command line interface instead of a tuned browser UI.
That is a great way to put it.
You're technically accessing the same internet, the same underlying data, but the interface isn't designed to return the results in the formatted, interactive way you actually want.
That captures the dynamic perfectly. The base model has the knowledge, but the instruction-tuned model has the interface. It understands the user assistant dynamic. Without that specific fine-tuning phase, zero-shot prompting simply wouldn't work as an engineering strategy.
Okay, so we have the right tool now, the instruction-tuned model.
Yeah.
We know it works by activating implicit pathways. But having the right tool doesn't mean you automatically know how to wield it. If you just type a vague wish into an API, you're going to get a vague output.
Garbage in, garbage out.
Always.
No.
So let's talk about the actual engineering of task framing. How do we write a zero-shot prompt like an engineer rather than an amateur?
It requires treating your prompt with the same rigor you apply to any code base. When you're relying entirely on the model's implicit knowledge without any examples to guide it, your instructions have to be bulletproof.
Bulletproof instructions.
There are 4 key pillars to structural task framing: using conventional task names, specifying output formats precisely, defining edge cases, and minimizing overall ambiguity.
Conventional task names makes total sense based on what we just talked about. If you're trying to activate a pre-existing pattern, you need to use the name of the pattern as it likely appeared in the massive training data.
Exactly. Don't say, make this text shorter and punchier. Say, summarize this text.
Because summarize is the conventional NLP task name.
It goes even further than that.
Yeah.
If you don't use the conventional task name, the model doesn't just fail.
It tries to guess, right.
Right. It actively tries to guess your unconventional meaning. It starts pulling from disparate, weakly connected pathways in its network, which is exactly how you induce hallucinations.
Wow.
You're querying a highly specific index. You have to use standard search terms. Treat the prompt like writing a strict API request. You wouldn't use vague language in a REST payload. If you want a JSON object, you specify JSON. If you want a list of strings, you define that structure.
And defining edge cases. That is pure software engineering.
It really is.
Think about a data pipeline. What should the model do if the text you provided doesn't contain the answer you're querying for? Like, a bad prompt says, extract the user's email from this transcript.
Right.
But what if there is no email? The model might just guess one. Or write, I couldn't find an email, which then gets passed downstream and completely breaks your database schema.
Exactly. Your parser just crashes.
Yeah. A good engineered prompt says, extract the user's email. If no email is present, output the string in your L. You're handling the exception before it throws a massive error in your pipeline.
Minimizing that ambiguity is the overarching goal of task framing. Zero shot means you're providing zero calibration data. The model has nothing to latch onto except your specific word.
So if your words are fuzzy.
The output distribution is going to be fuzzy.
Here's where it gets really interesting, though. We've talked about task framing, which feels very logical, very programmatic. But then there's another technique that sounds completely unscientific to a lot of engineers.
Oh, let me guess. Role prompting.
Role prompting. Starting your prompt with, you are an expert developer, or you are a senior data scientist. I'll be honest, the first time I saw that, I thought it was a joke.
Most people do.
It sounds like a psychological trick you'd play on a human. A pep talk. Come on, buddy, you're an expert. You can do it.
It does sound a bit like digital therapy, but the reality is far more mechanical.
Right. If we look at it mechanically, it's not a pep talk at all. If the training data is this massive, multidimensional vector space of information, saying you are an expert Python developer is literally setting a pointer to a specific high-quality cluster of data in that space.
I love that framing, and it's mathematically accurate. Think about the sheer variance in the training distribution. The model has ingested code from absolute beginners posting broken scripts on forums asking for help.
Stack Overflow nightmares.
Exactly. But it has also ingested pristine, highly optimized code from top-tier open-source repositories. Both exist in its memory. Both have associated linguistic weights.
So if you just say, write a Python script to do X, the model might just average out all that data and give you something incredibly mediocre.
It will likely sample from the dense center of that distribution, which is distinctly average. But role prompting is a mechanical way to bias the output. By establishing the persona of an expert Python developer, you're heavily weighting the probability matrix toward the linguistic and structural patterns associated with high-quality professional code.
You're forcing it into the good neighborhood.
Exactly. You are actively restricting the search space to the good stuff.
It's a heuristic filter. A filter applied right at the start of the generation. That makes so much more sense than just pretending the AI has an ego we need to stroke. You're defining the subset of the standard library it's allowed to access.
And because token generation is sequential, that initial filter is everything. You're shaping the probability distribution of the very first token it generates, which then cascades, altering the probabilities of the next token, effectively shaping the entire output.
This is all incredibly powerful. The standard library of implicit patterns, instruction tuning giving us the user interface, task framing, tightening the API request, and role prompting filtering the vector space.
It's a solid stack.
It feels like you could build anything with just zero shot. But every good engineer knows their tool's constraints. A tool without limits isn't a tool. It's a magic wand, and we already established we aren't dealing in magic. So what does this all mean? Where does this seemingly magical zero-shot approach actually break down?
It's a critical boundary every developer hits eventually. Zero shot reaches its hard mathematical limits in three specific areas: unfamiliar output formats, highly specific domain conventions, and complex reasoning chains.
Let me test that first one. Say I'm building an internal enterprise app. It requires a highly specific, heavily nested, proprietary JSON schema.
Okay.
Something my company invented yesterday, something that definitely does not exist on the public web. Is zero shot going to fail me? Even if I describe the schema perfectly in the prompt using all the task framing rules we just discussed.
This raises an important question. An answer is yes. It is highly likely to become unstable
Why? I told it exactly what to do.
because you're asking it to generate a structural format it hasn't mapped internally. Those implicit pathways we talked about. They aren't strong enough to carry the model through a rigid novel structure without a visual guide. Let's say you ask it for this custom nested array. Because it's predicting text sequentially, the latent probability of a standard comma might be 49%, while the probability of your required proprietary bracket structure is only 20%.
I see.
So it hallucinates a standard JSON response instead of your custom one, forgets a closing bracket, and your parser crashes.
And in software engineering, if a data schema works 80% of the time, that is a 100% failure rate for your application.
Precisely. The same limitation applies to domain-specific conventions. If you're asking it to write a legal contract using the highly specific boilerplate required by a niche regulatory body in one specific jurisdiction.
It's just going to guess.
Yet the model knows what a contract looks like generally, but it doesn't have a deep enough implicit groove for that hyper-specific convention to reliably zero-shot it. Yeah. The weights just aren't there.
And what about complex reasoning chains? I feel like I see this constraint pop up all the time. You ask an LLM a logic puzzle or a complex multi-step math word problem, and it just confidently hallucinates the wrong answer immediately.
That's the third hard limit, and it comes back to the architecture. Zero-shot struggles with complex reasoning because the model is generating tokens sequentially. It doesn't have an internal monologue.
It can't think before it speaks.
Exactly. If the problem requires 5 steps of intermediate logic to arrive at the correct final answer, and you ask it to just output the final answer via a zero-shot prompt, it doesn't have the mental workspace to compute those steps silently. It's essentially forced to guess the most probable final number based on the prompt's phrasing, which is almost always wrong.
It's trying to leap from A to Z without traversing B, C, and D. The standard library doesn't have a pre-computed answer for every unique math problem, so if it can't compute the intermediate steps, it just falls flat.
The training data simply isn't strong enough to carry the model through complex multi-step logic without a structural guide to follow.
So as an engineer, when I inevitably hit that wall, when I need my proprietary JSON schema to work flawlessly, or when I need the model to parse complex multi-step logic, what is the immediate solution? If Zero Shot is at its limit, how do I actually build this app?
Well, if Zero Shot hits a wall with complex reasoning and unfamiliar formats, the immediate architectural solution is few-shot prompting.
Few shot. So we're transitioning from telling the model what to do to showing it what to do.
Yes,
As an engineer, that's completely second nature. Providing a few examples of inputs and expected outputs is basically the same mental model as writing unit tests.
that's a great way to think about it. Few-shot prompting is essentially the most powerful zero-shot amplifier. When the implicit patterns in the weights aren't enough to guide the output, you explicitly map the pattern in the prompt itself.
But there are very specific parameters for this, which I find fascinating. It's not just about throwing a giant dictionary of examples into the prompt payload. The sweet spot for few shot is 3 to 8 examples.
That's right.
Why not 50? I mean, if more data is better, why stop at 8?
It comes down to context window management and, more importantly, attention mechanism dilution.
Attention mechanism dilution.
Right. If you provide fewer than 3 examples, the model might not fully lock onto the pattern, especially if it's a highly complex, nested JSON format. But if you provide 50 examples, you aren't just burning through your token costs. You actually risk confusing the model.
Because the model's attention mechanism doesn't just read linearly, right? It calculates the mathematical relationship between every single token in the prompt.
Exactly. If you throw 50 examples at it, the mathematical weight of your actual final instruction gets diluted in the noise of all those examples. The model might over-index on a tiny anomaly in example number 42 and completely ignore your core request. 3 to 8 examples gives the attention mechanism enough data to lock onto the pattern without drowning out the instruction.
3 to 8 is the golden ratio. But it gets deeper. Example order matters more than you'd think.
This is a critical engineering detail. The model processes text sequentially, and there is a documented recency bias in its short-term memory.
Recensive bias.
Yeah, the example's positioned closest to the end of your prompt, right before the actual live task you want it to perform. They have a mathematically heavier influence on the output. If you have examples of different edge cases, the order in which you present them will subtly bias how the model approaches your live input.
That's wild. You can't just dump examples randomly. You have to curate the sequence, which leads directly to the most advanced strategy for handling this at scale, the dynamic selection of examples based on the current input.
Right. If you're building a large application, you don't hard-code the same 5 static examples into your prompt for every single user request.
That would be rigid.
Instead, you use a vector database. When a user submits a query, your system fetches the 3 to 8 examples that are most semantically similar to that specific user's current input, and you dynamically inject those highly relevant examples into the prompt before sending it to the LLM.
That's incredible. You're basically building a custom, hyper-targeted micro-training set for every single API call on the fly. You're giving the model exactly the context it needs to bridge the gap between its implicit knowledge and your proprietary formatting. But, well, we're getting a little ahead of ourselves. That's going to be the deep dive for our next session.
It's the logical progression. You start by mastering the zero-shot baseline, understanding the model's native implicit capabilities, and then you scaffold it with few-shot techniques only when necessary.
Let's wrap this up. We've covered a huge amount of ground tonight in this late-night session. We started by demystifying zero-shot prompting, realizing that it's not pouring answers from the void, but activating implicit patterns learned from a massive training corpus. It's calling the probabilistic standard library.
We established the absolute necessity of using instruction-tuned models, the transformational shift where researchers adjust the weights to give these models a usable, assistant-like interface.
And we looked at the strict engineering of task framing, conventional names, precise formats, handling edge cases with NLL values, and minimizing ambiguity. We treat the prompt like a strict API request. We reframed role prompting not as a silly psychological trick, but as a mechanical pointer setting a heuristic filter to bias the model toward a high-quality distribution in its vector space.
And we define the boundaries. We know exactly where zero-shot fails. Unfamiliar formats, niche domain conventions, and complex reasoning chains that require sequential logic, which sets us up perfectly for the transition into few-shot prompting, where we bring our own curated examples to the table to overcome those limits.
Prompt engineering isn't magic. It's a deterministic skill. It's about minimizing ambiguity, understanding your tool's mathematical constraints, and knowing how to traverse the massive architecture of the model's training distribution. You are in control of the prompt. But before you turn back to your codebase, I want to leave you with a final thought to mull over. We talked about role prompting. We talked about how saying you are an expert developer mechanically biases the model toward high-quality professional text from its training distribution. Well, if that's true, what happens if you explicitly role prompt it to be a terrible, inexperienced coder who constantly makes syntax errors? Are you just as effectively traversing its architecture to generate perfectly flawed, bug-ridden code? The model has read the absolute worst code on the internet just as thoroughly as it has read the best. What other unseen personas, what other hidden, deeply bizarre distributions are just sitting there in the dark of that neural network, perfectly preserved, waiting to be activated by exactly the right words?